Hello, this is Jeffrey Fox, the instructor for cloud computing and big data or data engineering, and we have part O of the introduction to this course. Lots of parts in there. This introduction is divided into many parts because each part is only around 10 slides and there are over 200 slides here. All right, here we go. This particular segment's on storage. And this is not a very deep discussion. It's an overview of some issues, like the approaches to storing data on clouds in very broad fashion, and some discussion of the difference between file systems, repositories, and a comment or two or one on data lakes. So here we go. All right. So we've already talked about MapReduce with Hadoop, and that's a unique processing model. I've stressed the revolution of clouds is not just the way infrastructure is made available, it's also the wonderful software, which is strikingly better than the previous generation software. Another area where clouds are different from previous approaches is in the data model. Now, if we look back at just a few years, everything was very straightforward. Enterprises used databases, and Oracle made a fortune. Actually, it still makes a fortune because enterprises have not changed their old way of doing things. They have added new ways which do not necessarily use databases. Science did not use databases. It didn't really need them as well. It did not have transactions. It had large chunks of data like images and things like that. It didn't really want SQL queries. SQL wasn't terribly optimized for science. And it used custom software to access the information of interest, such as trying to access the events which the Higgs boson produced. There was an exploration of object-oriented databases by the particle physics community, a very serious one. They used objectivity, among others, but that failed. They did not find it useful compared to the traditional approach of lots and lots and lots of files. Now, Web 2.0, which we now realize has gone out of fashion as a name, but sort of meant search and initial social media, has huge data sizes, much, much larger than science. Remember, science is hundreds of petabytes. The real world is 10 or so zettabytes, whereas zettabyte is 1,000,000 petabytes. So we have huge data sizes, and also databases are not so suitable for Web 2.0 just for size issues. Databases don't really manage a zettabyte of data very efficiently. And so somewhat also it's essential to run Web 2.0 data in parallel because there's what I call parallelism over users and parallelism over usages. Both are needed, and databases are not so good. And this led to these NoSQL approaches, or not only SQL, sometimes people like to say, and various parallelisms where MapReduce with Hadoop is in the context of the system called Hive, it is effectively a database and a competitor to Oracle databases because it supports SQL. Now, if you think about the way data is organized, if you look at if you have a Windows system still or an Apple system, you will have directories. And you think about directories because you have Windows Explorer, which explores the directories, which is a hierarchical organization. And you actually guess what is in your file from the name of the directory and the name of the file. So I will find this by looking for a file name ending in O, because this is part O. I will look for the directory corresponding to this class, and maybe a subdirectory corresponding to resources or slides or what have you, or maybe one to this particular introduction. And so this approach was generalized to share files across many computers. That's what things like Lustre do, although there are many systems competitive to Lustre. And then we would use Unix I/O, which almost now goes back to the beginning of time, and we access this data either like Box or Dropbox. Actually, OnCourse has been replaced by Box at IU, and so that's one approach. But that's sort of not how clouds do it. They probably do it like that at the lowest level. Um, and the Google file system, which is seen in the open world as the Hadoop file system, this was a very early development, and they just realized that they had to have very efficient parallelism. And so the Google file system and HDFS are designed to support parallelism where lots of disks are running simultaneously, and that's because disks are slow. If you want to get high performance, you better put a disk on every computer and run those disks in parallel. And other file systems also allow parallelism, but the Google file system is simpler, and probably because it's simpler, if you use it correctly, exploiting its simplicity is also more efficient. Another important development was object stores like Amazon S3 or OpenStack Swift. And they have an easier interface to use than traditional file systems because you're accessing objects and you're not trying to navigate a hierarchical labeling system, because objects may or may not. I mean, if you use in the beginning of the web search, Yahoo had these web search systems which are hierarchical. Knowledge was organized hierarchically, but that's not how it's done in search engines today. You just type the information you want, and the Google or Bing search engine just looks for it, whether or not, and it probably will be stored hierarchically, but it's not necessarily stored hierarchically. Databases are still very important, but they build on top of these lower level systems, and they have different access semantics and also different approaches to consistency. Because if you're tackling these giant big data problems, you have to have worldwide distributed data systems, and databases are not so easy to keep consistent across the world. So here we have these traditional approaches, directory and file names, and we have databases with tables and indices. Indices are good in all these systems. You must have indices, because that's a search. That's just making the search easier. Then we have these NoSQL approaches like HBase, Dynamo, Cassandra, MongoDB, CouchDB, React. They differ by the languages they use, what they support, whether they support documents or column stores, document stores, column stores, graph stores, and they just depend on the structure of the data. You have very simple things like Azure Table and SimpleDB, and these often are built on an HDF-style storage, and they store everything in a distributed, scalable fashion. That's why we're doing it. They don't necessarily have fixed schemas, and this gives you web-scale storage. Or else even data center scale, a database was not even likely to be good at a data center scale storage. And as I said, depending on the structure of the data, you use different type of stores. And often Hadoop is used to process this. You link these nifty things to Hadoop. So, a critical idea is co-location of data and computing. And I've already mentioned that actually with the owner computes rule in parallel computing. The owner compute rule says, find where the data is. That computer which has the data does anything you want to do with that data. This is a well-known principle, that you bring the computing to the data, not the data to the computer. So it's pretty important. And another change is computing, namely the original model for data, which was sort of NASA had data archives. Well, they were data archives. They were not compute. They did not offer computing on the data. And a huge change today is that everything that's being built is the combination of a computer, in the MapReduce parlance, doing the maps, and the data. And that's a very important change, which has not even been realized today by some of the government repositories. Another interesting feature is sharing, because we have to share resources. And again, this model, as science gets to big data, the previous model, where you just downloaded your data to a personal cluster, is not effective. At least it's sometimes effective, but often is not effective. So we need a remote computing, because we want the scientist to identify, or the business person to identify the data they want and then do the computing on that data. They do not want to have to, they can move the data once or twice, but they can't move the data lots of times. That is ineffective. And we have to reconcile the distributed data, because the data is always distributed. I point out all the Web 2.0 data is distributed, because it comes from people around the world. But the analysis is shared. The data has to be shared. The data from different parts of the world have to be put together and shared to do the analysis. Another important issue is you might have two sorts of data, like the, I don't know, data on climate simulations and data on environmental sensors, and you're trying to study climate change or something. So those two databases correspond to different communities and are likely to be stored in different places. So how do we tackle that issue? That each discipline will have its own, the traditional model is each discipline has its own data set. Now, when the model was you just downloaded it, the person doing the analysis did the integration of data from different sources. But that doesn't work when you have each of those sources has petabytes or even exabytes of data. And so we can expect data repositories of the future will have data stored, which is hopefully cheap to access and stored cheaply, and elastic cloud analysis. And it's elastic because we don't know how much analysis will be used. And at least some models which Amazon, for instance, has used, is they store the data, say, NIH genomic data for free, but they charge you to do the computing. That sounds a sound model to me. All right. I pointed out that each discipline has its own repository. EOS disk is Earth observation, GEMBAC is genomics, NSIDC is polar science, IPAC is infrared astronomy, LHC and the Open Science Grid do computing storage for particle physics. And as I keep saying, these traditional approaches tend, I mean, actually the particle physics one does attach the computing to the data storage. So because they were a relatively recent one, they got it right. And it's also true that those LHC events have huge amounts of computing, more than some of the other fields. And we have the huge volume of data. We have distributed instruments such as gene sequencers are scattered all over the world. And we have intense computing in, say, the NIH gene sequencing case like BLAST. So we need lots of computing. And that's bound to be a cloud, but it's okay if we did everything on Amazon, because Amazon's big enough to do everything. As is probably Microsoft or Google. They may not be as big as Amazon, but they're probably big enough to do almost any practical problem. And plus, if it's stored on Amazon, then all the disciplines are stored on Amazon. So it's a straightforward solution. But I think people are reluctant to take that solution because it says it gives up. It says, well, industry's one, they're so big we can't compete. So here's a little technical comment about how, say, this is how the data at IU is stored. You have compute clusters like Big Red 2 or CAST. Then you have a storage system, which has got data and some sort of storage controller, which is presumably a computer of some sort. And then you might have a back-end storage. It might be hierarchical. These may be disks and these might be tapes, but the compute clusters are mainly to do computing. They have small amounts of onboard disk, and they always get the information from back-end data. And this is actually has one nice feature. If you have this back-end data, you can then store it with other clusters. So we can have 10 clusters here. And that's actually pretty convenient. When this contrasts with the alternative, which is to store the data on the compute cluster. That's illustrated here with data parallel file system like HDFS or GFS. You have just you take out all your files, you break them up into blocks, you probably replicate the blocks for fault tolerance. I think it's done 6-way by Amazon, and then that's the model. Here's the compute node, and we don't have data centers owning the data. We have compute nodes owning the data, and that's a pretty different model. And for some problems, that's hugely efficient. It's not obvious you need any archival storage in this case because the fault tolerance is done by replicating the data. And the computing is brought to the data. Because here we have the computer and it's attached to the data. Very clearly done. On the previous slide, we would have to use we have to have fast internal networks to bring the data from the back-end shared storage to the compute node. That may or may not be practical. It's unclear. Here is, so I would say it's pretty important to note that clouds are different, and quite how that difference is translated into practice in fields like science, which has never done things quite like this, is not obvious. Here's a final slide from Gartner about data lakes, which is just sounds a nice term, and it's effectively is one approach to moving data. So you sort of move the data once. You have all your back-end stores, and you say, well, I'm going to make a lake. That lake will have all the data swimming in it, and you can access. We will put everything in that lake, and that lake is not the permanent storage of the data. It is the temporary storage in the data. And it's meant to be a lake where you can just plonk on your Hadoop or Spark or MPI analysis program and do it on the lake. And its lakes are not, I think, have just come along. Gartner is slightly skeptical that through this year that only 10% of organization will actually know how to use a lake and have rules about what lakes do. And then it says also most of the deployed lakes will become useless. Because they have been, the definition of what you have to do is so vague that you have to put all data there in all forms, and that just will saturate your lake will fill up, and then it's not useful. And so they claim you should position your data lake as a source of new insights, but not as your only storage system. So I would say I'm not a great expert on data lakes. It's an interesting idea because it is quite important, I think, to realize you might have to move the data 1 or 2 times. That is better than moving the data every time a user wants to use it. Okay, that's the end of this section on storage. Thank you very much, Jeffrey Fox, signing off from Part O.